Hello, everybody. Welcome back. Today we're going to be looking at subunit 9.6, which is on the free energy of dissolution. If you are following with my videos, I'm going a little bit out of order here. To me, it makes more sense to put this topic right after 9.3. So let's get started. All right, so first of all, what do we mean by this word, dissolution? That's just a fancy word that means the process of a solute dissolving in a solvent. And if you think back, way back to when we first looked at our solubility rules, there were rules that told us that some salts would be soluble, others are described as slightly soluble or insoluble. And the question is, why is that? And it comes down to thermodynamics. For me, it makes sense to put this subunit right after 9.3 because we have just talked about the meaning of delta G, that Gibbs free energy. And if you guys will recall, if delta G, the change in Gibbs free energy, is negative, that indicates a thermodynamically favored process. And if delta G is positive, then it's not a favored process. So salts that are soluble because the change in Gibbs free energy of the dissolution process comes out to be negative. Those that have a delta G that is positive would be described as slightly soluble or in some cases even insoluble. And what we're going to talk about, we're going to do a little bit of review back from Unit 3, but whether a delta G of dissolution is negative or positive is really down to what's going on with the change in enthalpy and the change in entropy. So we're going to look at each one of those individually. So let's start just reviewing. Back from Unit 3, I used this same image. What is physically happening during the process of dissolution or formation of a solution? So in this graphic, we have sodium chloride as the solute, water is the solvent. And if you'll recall, this process of dissolving occurs in 3 steps. Step 1 is breaking apart the solute. Step 2 is expanding the solvent. And step 3 is the interaction between the solute and the solvent. And in the case of an ionic solute, we see, as we're seeing in this image, that water forms this almost cage of molecules around each ion. Let's review the change in enthalpy associated with each step. So step 1, we're breaking apart the solute. Okay. In this specific example, that would be breaking ionic bonds, ion to ion attraction. But no matter what the solute is, that first step is always going to be an endothermic delta H. Remember, it takes to break. Okay. So step 1 in that solution formation, always going to be endo. Step 2, we're expanding or breaking apart the solvent particles from one another, also going to be endo. It takes to break. In this circumstance, we're breaking London dispersion, dipole-dipole attraction, hydrogen bonding between the water molecules. And again, that is always going to be an endothermic heat change. Step 3, if you'll recall, is kind of the questionable one because it involves how do the solute and solvent interact with one another. If solute and solvent have a strong attraction for one another, then that third step is likely to be exothermic, whereas, like oil and water, not going to have as much attraction. That's likely going to be an endothermic process. But here's the thing. The heat change associated with the dissolution process is all three of these steps added together. So if when we add these three steps together, they're overall, and let's focus in on that third step there. If the solute and solvent are going to have a strong attraction to each other and the magnitude of that exothermic heat change in step 3 is very large, then that's going to sort of dominate over steps 1 and 2, and overall, the delta H for the whole process might be exothermic. Or, if solute and solvent don't have a super strong attraction for one another, and step 3 is endo, well then when we add all three together, it's definitely going to be overall endothermic. So it's really that third step that sort of determines whether the overall change in heat for the dissolution process is going to be endo or exo. It depends. Let's talk about the change in entropy. Now, because this is the process of a solute breaking apart, typically your delta S for these processes is almost always going to be positive. So let's put this all together. Okay, this equation we've seen before. It's on your formula sheet. We talked about it in Unit 9.3. It brings the change in enthalpy and the change in entropy together. And this chart in front of you should look familiar. We saw this back in 9.3. As I said, the dissolution process is almost always going to have a delta S that is positive. Now, the column in front of you that says delta H, remember that in this circumstance is meaning the delta H of all three of those enthalpy steps added together in the dissolution process. If all three steps added together overall end up being exothermic, then we're dealing with a solute that will always be soluble. These are salts that in our solubility rules would be described as soluble. They're soluble because an exothermic delta H and a positive delta S, when we plug it into that equation above, no matter what the temperature is, will always give us a negative delta G. And that's what really determines whether a salt is soluble or not. Now look at the second row. If the delta S is positive, and when we add those three steps together for the dissolution process, all three of those enthalpies together, and it comes out to be endothermic, from Unit 9.3, we would say, oh, well, that's going to be favored, but only at high temperatures. So in this case, it kind of depends. It depends on the temperature, okay? Can you have salts that will dissolve with positive delta H and positive delta S? Yes. If you have the temperature high enough, you can get maybe some of it to dissolve. So it depends. But the take-home message here, guys, is just like any other chemical reaction or physical process, the process of a solute dissolving, yes or no, is dependent upon the signage of delta G. So that was a relatively quick little topic. I hope you guys have learned a little something today, and I look forward to seeing you next time.